Good morning everyone. Today we'll be talking about Borel sigma field. So Borel sigma field has a lot of importance in probability theory. In fact, whatever we study in terms of probability, everything would be related to Borel sigma field. Okay. So Borel sigma field is defined as a minimal sigma field generated by any class of intervals on real line. So what are the different classes of intervals on real line? So let me consider different types of intervals on real line. So you know the definition of interval, right? So interval means it has to be kind of a connected set, so there shouldn't be any gap in between. Okay, it should be a connected set on real line, there shouldn't be any gap in between. So technical definition of interval, how would I define an interval? Have you ever given it a thought? I mean, if we see an interval, yes, we easily realize, okay, this is an interval, this is not an interval. But how do you define an interval? So whatever we said here can be captured in words. It shouldn't be disconnected. Means if I have any 2 points, if I know that, okay, this is say A1 and this is B1 and I know that they belong to interval, then every point in between them should also be an interval. Okay. So let me repeat. So if, okay, let us start with some, let I be a subset of real line. We say that I is an interval. We say that I is an interval if for any A1 B1 in I A1 less than X less than B1 would imply X belongs to I. Okay, for any or for every pair A1 B1 in I, if X is between A1 and B1, then X must be an interval. Okay. So what are different types of intervals? The simplest one is open interval, finite open interval. Then the next one can be finite closed interval. The next one can be semi-open, semi-closed, or neither open nor closed, whichever way you want to say. Okay. So these are 4 types. So these are basically finite intervals. Now when I say finite intervals, they are not finite sets, because every interval we know is an uncountable set. There are too many things in there. But when I say finite interval, I mean finite in terms of length. Okay. So the length is b minus a, it's a finite number. Okay. And then there are infinite intervals. For example, a to infinity, closed a to infinity, minus infinity to open b, and minus infinity to closed b. On the infinity or minus infinity side, it will always be open because infinity is not a real number. Similarly, minus infinity is not a real number. So you can't include them in interval. We are talking intervals as subset of real lines. Okay. So these are 8 different types of intervals. Are they related to each other? When I say related, I mean in terms of the set relationships that we have been talking about. That is, can I express one interval as say complement or unions or intersections of other intervals? Okay. So let us see a few examples. So suppose I want to see if this open interval AB can be expressed in the form of closed intervals AB. Okay. So one option can be, I want open interval. So this is A, this is B. So if I take maybe closed intervals inside and if I go on increasing them in such a way that increasing their size in such a way that it touches B, it touches A, but it never actually reaches A or B. Okay, it always finishes just before A or just before B. Okay, actually when I say just before A, it means just after A. Okay, so if I define intervals of the type A plus 1 by n and B minus 1 by n, and if I take union over them, okay, then our claim is it becomes AB, because this is going to 0, so the left hand end point is going almost close to A. This is also becoming 0, so this is also going to B. But we need to prove this. How do I prove this? If I want to prove two sets are equal, I have to actually prove that they both are subsets of each other. So if I take x in AB, I have to prove it is in here. It is in this union. And if I take some set from union, I have to prove it is in AB. So consider x belonging to AB. Now x is in AB means x is somewhere here. We have to prove that x is in the union of the right hand side sets, means we have to prove that x is in at least one of the closed intervals of the type A plus 1 by n, B minus 1 by n. Okay. So if this is x, I need to have at least one A plus 1 by n here, so that I can get the corresponding set. Okay. On the other hand, if x is close to B, I need to make sure that I have some B minus 1 by n here between x and B, so that x would go in this set. Okay. So depending on whether x is close to A or whether x is close to B, I need to appropriately choose my n. Okay. So let us try first the case where x is close to A. Okay. So case 1, x minus A is smaller than B minus x, because the distance between x and A is x minus A and distance between x and B is B minus x. So now I have to come up with some n such that A plus 1 by n is less than x. So what is meant by that? Let me do some rough calculations. A plus 1 by n should be less than x, means 1 by n should be less than x minus A, that is n should be greater than 1 upon x minus A. Is it possible to get some n which is greater than 1 upon x minus A? Yes, Archimedean property tells me that it is possible, because set of natural numbers is unbounded. It's not bounded above, so I can get as large n as I want. Okay, so this was my rough calculation. My formal proof is here. So consider n naught, which is ceiling of 1 upon x minus A. What do I mean by ceiling? Actually, I am writing in terms of R command. If I want to write in mathematical terms, it would be integer part of 1 upon x minus A plus 1. Okay, so n naught is the smallest integer just greater than 1 upon x minus A. Okay, so basically you are rounding up. So with this n naught, what I know is n naught is greater than 1 upon x minus A. Therefore, x minus A is greater than 1 by n naught. X minus A is greater than 1 by n naught means x is greater than A plus 1 by n naught. Okay. X is greater than A plus 1 by n naught. I also need to prove that x is less than B minus 1 by n naught, because then only it would be in the interval. So let us try by contradiction. So suppose x is greater than B minus 1 by n naught, what would it mean? It would mean that x plus 1 by n naught is greater than b. Okay. It would also mean 1 by n naught is greater than b minus x. Okay, 1 by n naught is greater than b minus x. So, considering this and this, what do I get? I get that 1 by n naught is in the middle. So, I get that x minus a is larger than 1 by n naught is larger than b minus x. Okay. But we know that is not the case. We know that x minus a is smaller than b minus x. That's what we started with. Therefore, this is a contradiction. Okay. So, this is a contradiction. This is a contradiction. And we will conclude. So, this is a contradiction. Hence, we will conclude that x is less than b minus 1 by n naught. Therefore, we have proved that x belongs to closed a plus 1 by n naught, b minus 1 by n naught, and therefore x belongs to the union of such sets. Okay, x belongs to union of such sets. As a result, what we have proved is the left hand side is subset of right hand side. That is, we have proved AB is subset of union a plus 1 by n, b minus 1 by n. To prove reverse way, it is quite easy. I have to take x coming from union a plus 1 by n, b minus 1 by n. X is in union means it is in individual sets. So, x belongs to one of the individual sets at least. A plus 1 by n, b minus 1 by n for some n. Okay, x belongs to this interval for some n. This implies that a plus 1 by n is less than or equal to x is less than or equal to b minus 1 by n. And of course, this means that a is here, b is here. Therefore, x belongs to open AB. Okay. So, we have proved both ways. Hence, we have established that AB can be expressed as union of closed intervals. So, open interval can be expressed as union of closed intervals. Okay. Now, the homework is going reverse way. So, homework is, can you go reverse way? Means, can you express closed AB in the form of open intervals? Okay, let me give you some hint. Now I want closed AB in the form of open intervals. So if I start with open intervals from inside, it's not going to help, because finally also the limit, the marginal points won't be included. So this is not going to help. So what I probably have to do is, I want closed AB in terms of open intervals. So start with something like this and maybe go on decreasing their size such that every interval still contains A and B. Okay. So try to think in this direction. Now let me try one more thing. Let me try to express one finite interval in the form of infinite intervals. Okay. So suppose I want AB to be expressed, I want AB to be expressed in the form of intervals of the type minus infinity to B. Okay, because this seems slightly difficult. So how to do that? Expressing finite interval in the form of infinite interval seems difficult. So minus infinity to B is interval of this type. And what I want is I want AB. So how should I proceed? Think. Of course, I can take minus infinity to A. Now, would that help me? So, minus infinity to B is going to be this portion. Minus infinity to A is going to be this portion. So, it's kind of removing minus infinity to A from minus infinity to B. Kind of like that. But of course, I don't want A to be removed. Something like this. Okay. Because finally I want open AB. So first let us consider whatever I said just now. So from minus infinity to open B, if I kind of subtract minus infinity to open A, I would be left with closed A and open B. Okay, I would be left with this interval, but A is included because I have not subtracted A. Okay, so when I say subtract, we have to basically take intersection with the complement, right? Subtracting of a set means taking intersection with the complement. So here I will get closed AB. So I need to somehow deal with closed AB also to convert it to open AB. But for this, the earlier trick can help. If I get maybe closed A plus 1 by n to B, and if I take their union, this would be open AB, because A plus 1 by n will go closer and closer to A. Okay, so instead of subtracting A, let me subtract A plus 1 by n, minus infinity to A plus 1 by n, something like that. Okay, these are all rough calculations. We have not yet written the formal proof. Now let us think in that terms. So consider intervals of the type minus infinity to A. Okay, I can take their complements also because our field relationships involves complements, unions, intersections. So consider an as minus infinity to A plus 1 by n. So an complement would be closed A plus 1 by n to infinity. Okay, n complement would be closed A plus 1 by n to infinity. And let B be minus infinity to B. So this is B, this is A. So B is something like this, set till here. Now n complement is something like this. So intersection of n complement with B would be this portion. Okay, so closed A plus 1 by n to open B. So intersection of B with n complement would be closed A plus 1 by n to B. Okay, and now I take union over all such intersections. If I take union over all such intersections, I will be left with AB. Okay, which is what I want. So we have expressed one type of finite interval in the form of unions and intersections and complements of infinite intervals. Okay, so now homework is try to find as many possible relationships as there are. homework is try to find as many relationships as possible between all types of intervals. Now let me define Borel sigma field. So what is a Borel sigma field? So let Ci be a class of intervals of type I. We have 8 types of intervals above, so I'll have C1, C2 up to C8. Let Ci be a class of intervals of type I. The minimal sigma field generated by Ci is known as Borel sigma field. Okay. The minimal sigma field generated by Ci is known as the Borel sigma field. Okay, minimal sigma field generated by Ci is known as Borel sigma field. Now what does it mean? We are saying Ci be a class of interval of type I, so we are not specifying whether it's type 1, type 2, etc. So basically this means that minimal sigma field generated by each type of intervals is actually the same. Class of each types of intervals is actually the same. And we denote it by script B, the Borel sigma field. Okay. How is this possible? The answer to that is in the earlier calculations. We can express every interval, every type of interval as unions and intersections and complements of other types of intervals. Hence, the minimal sigma fields generated by all of them are the same. Okay. So, for example, let me consider the same thing earlier, type 1 and type 2. So, let me try to prove sigma C1 is equal to sigma C2. Again, if I want to prove two sets are equal, I have to prove that they are subsets of each other. So, first let me try to prove sigma C1 is subset of sigma C2. What does it mean? It means that if I take any set from sigma C1, I should be able to express it in the form of, it should be in sigma C2. So for that, first we will try to prove C1 is subset of sigma C2. Okay. So we will try to prove C1 is a subset of sigma C2. If I want to prove C1 is subset of sigma C2, what does it mean? It means that type 1 interval, I should be able to express type 1 interval in the form of intervals from type 2. So I should be able to express type 1 interval in the form of type 2 intervals, means their complements, unions, intersection, etc. So type 2 is closed, type 1 is open. Okay. So we know. So open AB can be written as intersection of, union of open NB can be written as union over closed A plus 1 by n to B minus 1 by n. We proved it just now. So what does it mean? It means that A plus 1 by n, B minus 1 by n is in C2, because that is how we have defined C2. C2 is a collection of closed intervals. Therefore, union of countable union. So if you construct a field, countable union would be in that field, would belong to sigma C2, because it's the union of sets from C2. Therefore, AB belongs to sigma C2, and all these things are true for every AB in R such that A is less than B. Okay. Therefore, C1, the entire collection, is subset of sigma C2, because every open interval is in sigma C2. And therefore, minimal sigma field generated by C1 is the smallest sigma field. So it must be subset of sigma C2. So from here, what do I get? That this sigma field, sigma C2, contains C1. So minimal sigma field generated by C1 must be part of it. Okay. To prove the reverse way, I have to express closed interval in the form of open intervals. So consider closed. We know that closed AB can be written as intersection of A minus 1 by n, B plus 1 by n. This I have given you as homework, so you can prove it. Okay. Therefore, A minus 1 by n to, we know that A minus 1 by n to B plus 1 by n belongs to C1, implies closed AB belongs to sigma C1. Okay, because closed AB is countable intersection of sets in C1. So it is in sigma C1. Therefore, C2 is subset of sigma C1, because this is again true for every AB with A less than B. And therefore, sigma C2 being the minimal sigma field is subset of sigma C1. Hence, we have proved that the two sigma fields are equal. As I said, homework is to prove such equivalence for all the intervals. Okay, 1 equal to 2, 1 equal to 3, etc. I know that would be too many. 8 choose 2 proofs. So at least try to prove 1 to 2, 2 to 3, 3 to 4. So that 1 to 4 can be written as 1 to 2, 2 to 3, 3 to 4. Okay, equality of 1 to 4 can be written as this way by transitivity. Okay. Now that we have defined Borel sigma field, we need to define what is meant by Borel set. So every subset of R which is in Borel sigma field would be called as Borel set. Is called as Borel set. Okay. As a result, by definition, of course, all intervals are Borel sets, because all intervals are in the sigma fields generated by themselves. So they are all Borel sets. What can I say about singletons? Now, earlier in the sequences of sets, we have seen that if I consider something like this, A minus 1 by n to A plus 1 by n, and if I consider intersection, this gives me singleton A. Okay, so a singleton set can be expressed as countable intersection of open intervals. Therefore, all singletons are Borel sets. Okay, all singletons are Borel sets. Now, as soon as a singleton becomes Borel set, every finite set also becomes a Borel set, because every finite set I can write as maybe A1, A2, AK, So it can be expressed as union of singletons, finite union of singletons. Okay, so every finite set can be expressed as finite union of singletons, and hence it is also a Borel set. Similarly, every countable set can be expressed as countable union of singletons. So if I have a countable set A1, A2, etc., it can be expressed as countable union of singletons. Therefore, it is also a Borel set. Now, if I take uncountable set, I can express it as uncountable union of singletons, but we don't know whether uncountable union belongs to a sigma field. What we know is finite and countable. However, there are some uncountable sets whose complement is countable. So because of complementation, they would be Borel sets. So basically, co-countable sets. We have defined co-countable, right? Co-countable means a set whose complement is countable would be a Borel set. So by this logic, by number 4, my set of rational numbers would be Borel set, and by number 5, or because of the fact that Q is a Borel set, Q complement has to be in the same sigma field. So Q complement, that is set of irrationals, would also be a Borel set. Okay, intervals are already Borel sets, finite sets are Borel sets. If I consider any open set can actually be expressed as countable union of open intervals. Okay, we will maybe in the next lecture we'll try to give a proof for this, or you can search. So countable union of open intervals, every open set can be expressed as this. Therefore, every open set is a Borel set, and then every closed set by complementation, because it's a complement of open set, it would also be a Borel set. Okay, so what does it mean? It means that almost all the subsets of R are Borel sets. R itself being kind of omega for this all setup becomes a Borel set. Then positive part of real line being an interval is a Borel set. Negative part of real line being an interval is a Borel set. So almost every set that you can think of turns out to be a Borel set. But does it mean that all the subsets of R are Borel sets? No. There are certain subsets of R which are not Borel sets. Okay, but it's pretty difficult to construct them. From whatever we have listed so far, we know that they can't be open, they can't be closed, they can't be finite, they can't be countable. Okay, so some uncountable sets are non-Borel sets, means they don't belong to Borel sigma field. Plus they have to be neither open nor closed, because if they are open, they are in Borel field. If they are closed, they are also in Borel field. So some uncountable sets which are neither open nor closed are non-Borel sets, that is they don't belong to Borel sigma field. Okay, so I'll stop here. Try to do all the homeworks. Now you have lot of homeworks. Okay, so thank you.